Alrighty, day 2 of Leetcode. Given an integer n, okay, it's called Lexicographical Numbers, problem 386. Given an integer n, return all the numbers in the range 1 to n sorted in lexicographical order. You must write an algorithm that runs in O of n time and uses O of 1 extra space. Okay, so first example for n equals 13. Okay, so all numbers 1 through 13 and 10, 11, 12, 13 are before 2, 3, 4. Okay, so obviously I'm thinking it's just going to be a for loop, and then everything is going to be inside the for loop. Let's just, this problem is not that difficult to understand. It's just probably a little difficult to implement and get it within O of n time and O of 1 extra space. So obviously I think first we just need to set the outer for loop. So we're gonna be looping through for I in range. We're gonna start at 1. We're gonna end. The end is exclusive, so we're gonna end at n plus 1. And I think that's gonna be the outer for loop. And I think we might need a, I'm not sure if, I don't necessarily know how to get a problem within O of n space. Or what that necessarily means. Algorithm should not create additional data structures that scale with the input. Modify. So I can't create an array. That's difficult. If I'm not creating an array, what am I doing? Perhaps we should just try solving it normally first and then see if we can, and that will help us with the familiarity of the problem, and then we can try making the time and space complexity better. Yeah, I think that's so we're gonna have an array which keeps track of the results. So we're looping through all the numbers. And I don't think result.push I, and then let me just see result.sort. Let's just see what this does. Is it just add? Append. What? Oh. Sorted. Okay, it doesn't, okay, obviously, but how are we going to do this? This is not easy. I'm gonna return all the numbers in the range O sorted in lexicographical order. So somehow we need to do all this in O time. 10, 11, 12 needs to go before 2. I don't think it's an array structure. I don't know how to do this without arrays though. I'm honestly stumped. No recursive solutions. Oh yeah, 0. DFS, yeah. I need to learn that, don't I? Priority queue. Okay, I don't think I'm going to be able to do this without looking at the editorial, unfortunately. We need to create a list of integers from 1 to n and sort them in lexicographical order. Lexicographical order is similar to dictionary order, where the sequence is based on how words are arranged alphabetically. For numbers, this means sorting them as if they were strings. For example, 1, 0, comes before 2, because 1 is less than 2. Or 10, I guess. Yeah, it's not 1. The solution must be efficient with time complexity. This means directly without any nested loops. I'll slow it down. So obviously we can't use the result, or an array. We can think of generating numbers in lexicographical order by imagining how they appear in a dictionary. The first number is 1, followed by 10, 11, 12, and so on before moving to 2. The key is that smaller numbers starting with a particular digit should be fully explored before moving to the next string digit. So it's a tree. We start with numbers 1 through 9 as the roots of the tree. For each of these, we generate their children by appending digits from 0 to 9 as long as the resulting number remains within the range 1 through n. Start numbers 1 through 9 as the roots of the tree. Okay. For each of these, we generate their children by appending digits from 0 to 9 as long as the resulting number. Okay, that makes sense. Once we exhaust one branch, we move to the next root and repeat this process. In this way, interesting. Oh, so you do initialize another array. Is that constant memory, though? For each start, call lexicographical generate. Okay, so you iterate through the first digit, so for I range 1 through 10, because it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, and those are the roots. Okay. And we have another function here. Oh no, this is Python number. Self current number. Okay. If the current number exceeds the limit, recursion? So if it exceeds the range of what we're supposed to go to, you return it. Okay. And then we add the current number to the result. So consistent. Current number times 10. Okay, y, the next number equals the current number times 10 plus the next digit. Okay, so if our current number was like 5, right? That's our root. And we wanted to add, we wanted to try adding digits from 0 to 9, right? In order to do that, you can't just do the root 5 plus the next number, like 5 plus 2, because that would just be like 7. Instead, you have to do 5 times 10, so it would be 50, plus 2, which would be 52, which is what you want. So this just like adds another, I don't think decimal place is right, but just like another spot for the extra digit. That's pretty smart. Next, we check if the number is within the limit. Then we continue recursion. If next num is less than or equal to limit, then we do recursion. And if our next number is greater than the limit, we break. We break from this recursion. And up here, no, I don't think we need this. Start and and then result. Is that it? Oh. Okay, now we need to fully understand what this algorithm does and honestly visualize it. Okay, I'm confused how this is constant space. There's another. Okay, this is DFS. I want to understand actually both of these algorithms and how they work. Particularly how just DFS works. Oh, this is DFS. What? Okay. So these are the roots of the tree. This is where the chunk of the code lies. Self, current number, our current number is the root. The limit, so the max value we can have. And then the result, which is the list. Okay, this is our break case. If the current number we have, so say we're doing the same, say we're doing the example problem of n equals 13. If we're iterating through the roots, we have 1, right? And then once we get to 2, if we get to 2, right, this is the first thing that it reads. If the current number is greater than the limit, return. Obviously the current number is 2, so it's not greater than the limit. So it continues through this. Result.append the current number. So we're gonna add 2. And this is after all the 1s are read, right? This is after 10, or 1, 10, 11, 12, 13 are added to the array, or to the list. And then we append 2, right? But once we try adding more digits to 2, for example, 2 times 10, if our next digit is 0, it's going to be 20, but 20 is greater than the limit, so we can't continue recursively calling this function, and then we break. So all we're adding is 2. And this is the exact same process that we're doing with 3, 4, 5, 6, 7, 8, 9, and so on, right? So this is smart because it goes from the lowest digits to the greatest in lexicographical order. But this is crazy how it's O in time. I guess you're only doing one for loop, but it's recursively calling. Yeah, I'm a little confused with that, but let's make sure. that's just what this is kind of self-explanatory. We have another instance of limit here. I think the only instance in which this would be called to return is if n is less than 10, right? Because if it's greater than 10, say it's like 11, it's gonna call the 1 is gonna call this function. 1 is not greater than 11. Okay, 10. The next one would be 10. This would fit in there. So you would call it again, but 10 is less than the limit as well. 11, 12, yeah. But you need that for n is less than 10, so. Let me see if I'm right and it passes most of the test cases. There's only 27 test cases. Oh. It should pass most. Yeah, 22 out of 27. And the only ones that it doesn't pass is for n is less than 10, right? Cool. So if current num is greater than interesting, okay. Next number, and then if next number is less, then we can generate another one, see if interesting. Should I see if I can, if I understand this well enough, I should be able to create this from scratch. So let's see if I can. Okay. Alright, so go back to the problem description. Alright, so we have a result array. This is just going to contain okay. Now we're going to iterate through the digits, through the root digits, right? And for each, do we have to check to see if it's and then we're going to call self.generate I was going to call it generate children. That's not a good name. Or I guess I can just call it generate digits. We don't know what's going to be parameter in there yet. And then we return result. Okay, now we need to define generate digits. What we want is obviously the root number. We want the limit, so n. I guess we can call it limit in here and then call it n up there. And then the result array. But yeah, you have to. I think you have to specify. At least that's what the example did. List. Okay. And then, so we have our root numbers, 1 through 9. We first have to check whether the current number, I guess, yeah, we should change I with current number. And then I, n, and then result. We have to do self, right? So if current number is greater than the limit, then we just return. If it's not greater than the limit, then we add it to the array. It's going to do 1, 2. Yeah, we add it to the array. So result.append current number. And you can do that in Python. Yeah. After we append the current number, we have to add extra digits to the current number. I'm just visualizing the tree right now with the roots at the top, and then we go down a level and then add extra digits. So we're going to iterate for I in range 0 to 10, right? But we don't, I think it's default 0. So for I in range, next number is going to be our current number times 10. As I explained before, say our number is 5, the next number in lexicographical order would be 50. And you can't just do 5 plus 0 because that would just be 5, so you have to do 5 times 10, which would be 50 plus 0, which would obviously be 0, but it's the same process through all the digits. And then you just do plus I guess plus digit. And then we have to check if this is within our limit. If our next number is less than or equal to the limit, then hurrah, we got a new number to our list, right? But we don't append it here because we just call it recursively because it's going to add the number to the list when we recursively call it. So all we have to do is generate digits. Current number is the next number. Our limit is the same, and our result is the same. If our next number is greater than our limit, then we can just break out of this. Break out of the recursion. I believe this is correct. Okay, cool. Perhaps I should go through the example on the whiteboard if you have trouble visualizing this. So let's go through the example problem where n is 13 on the whiteboard. N equals 13. I'm going to draw the tree. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. These are our initial digits or our roots. Each one of these is going to have digits. So this is going to be 11, this is going to be 12, this is going to, oh no, it starts with 10. 10, 11, 12, 13. This is going to be in our recursion. So we start out with 1. We start out with 1. And then we call the recursive function. It adds 1 to the result. And then we iterate through the digits. These are our next numbers in our code. And we check to see if they are less than or equal to n. And say we get through all of these. These are good. These are less than or equal to n. But we get to 14. This is greater than n. This breaks out of the loop. And same with 15, 16, 17, 18, 19. But you don't go through 15, 16, 17, 18, 19. Because when you hit 14, you know that any extra digit is just going to be too large, so you break out of the loop, and that's what we have in the code. So that's also smart in minimizing the time it takes. Then for each of these, I explained if we try adding 20, this obviously is just going to be greater than our limit, so it doesn't work. And same for all of these. But you are able to add 2, 3, 4, 5, 6, 7, 8, 9. Very cool, very cool. You don't even necessarily need to think of it as a tree, though. And obviously, this keeps going, because when this is validated, this calls recursively again, and then it tries adding like 100, tries adding 101, etc., etc. But these are obviously above the limit. And same for all of these up until 14. Very, very cool. Okay. Now let's go back to the code. We can try seeing backtracking. This is interesting. So we have an initial array which stores the result. We have our current number. Then we iterate through n. We add the current number to the result. And then we see if the current times 10 is less than or equal to n. So this would start out as 0, or as 1. This would be 0. Current times equals 10. So this would be 10. If current times 10 is less than or equal to n, that would be 10. It is less than or equal to n with n equals 13. Then we add, so now our current is 10. Else, if current is greater than or equal to n, wow. Then you just go back. That is crazy. Current divided by, so you remove a digit. That is not intuitive at all, is it? What's approach number 2? Be how we organize. We initialize the current number as 1. Set up a loop that runs n times because we want to generate exactly n numbers. We add the current. Check if. Oh, I think this is the same. Yeah, this is the backtracking solution. I believe. Yeah, this is the backtracking solution. And it seems like it's faster. Or not necessarily faster, but it's better in space. So we have a result, then we have a current number. We iterate for each n, right? One times 0 milliseconds. So if current times 10 is less than or equal to n, so 10, honestly, let's just go, okay, so we're starting with, so for n equals 13, current equals 1, we add 1 to the list. Current is now 10 because 1 times 10 is less than or equal to n. Now we append 10 to the list, so now it's 110. $100, now it goes to 100, which is not within the limit. So now we go to this block of code. If current is greater than or equal to n, if current times 10, but it's not, because it's 10, right? So you add 1 to current. So now current equals 11. And you go along like that until you reach a spot where current is greater than or equal to n. So the first occurrence of that would be 14. And then you would do integer divided by 10, which would mean it would be 4, right? No. Fuck me. The result. Oh, the result. Oh my god, I'm dumb. The result would be 1.4, but it's modular, or it's integer division, so it would just be 1. It would round it down. So once it hits 14, it would be, current would now be once you hit the limit, or when it's greater than the limit, current would now be 1. But it was already 1. But you, oh my god, it's genius. But you then add 1 to it again. So now it's 2. Holy shit. No way someone thought about this. That's crazy. It's absolutely crazy. Anyways, that's it from me, guys. See you tomorrow.